Hello YouTube viewers, welcome to my channel Science Technology. In today's show, Rocket Monday, we're going to talk about SpaceX Starship troubles. So let's dive deep into it. Now, before we understand, are they actually in trouble or they are just like, just hype, you have to understand some historical context. Then you will get the idea whether they are doing good or doing bad. Well, failure is expected in prototyping and testing. If somebody is expecting a first prototype to just go YOLO, yeah, no, that's not like, no. And prototyping, again, that's why we do prototyping in order to figure things out. Like, Oppenheimer's dialogue, theory can only take you so far. So that is a reality of it. So let's look into SpaceX. So SpaceX started, the first puppy they made was Falcon 1, which was made in 2006, launched, and it went kaboom. And it went boom 3 times. And the fourth time in 2008, they successfully put payload into orbit, and that successfully got the contract from NASA. Stage contract, so to say, at that point in time. So that's how they started. And they wanted to make Falcon 5, but they were like, yeah, that's just a waste of time. So they directly switched gear to Falcon 9 version 1. And this puppy launched in 4 June 2010, and first flight was successful. And again, they have learned the fact that there will be a lot of oops events, so they were using Grasshopper to refine all of things. And because the Falcon 1 series had so many problems, they kind of made them very vigilant and very thorough, and that yielded Falcon 9 version 1, just like, I got this. And Falcon 9 series of rocket is surprisingly robust and surprisingly thorough. So that's the good part. Then we come to Falcon Heavy. That puppy was launched in 6 February 2018. This also had a very good first successful run. He just yeeted a Tesla Roadster in there. So that's the good part. Now, what about some big rockets? So big rocket, the biggest rocket successful one is Saturn V. Now Saturn V, engineers knew that Saturn V is too goddamn big to test everything in actual size. So they made Saturn 1, a smaller puppy, this one. And Saturn 1, and be mindful, this is in 1960s. So rocket is completely new technology. It's not like, okay, we have giant books and archives worth of data. It's like nothing. We have no idea how the heck that works. So they were like very methodic with it. So Saturn 1 was built, small puppy, and this was launched in 27 October 1961, and it went kaput 2 times. And after that, it reached orbit in 29 Jan 1964. So surprisingly good, given the fact that they have no idea. And again, no idea as in like, not enough things have happened for to have every single part sorted. But Saturn V was built, and this was built on launched 9 November 1967, and they had 0 failures. Surprisingly good rocket given the size of it. And yes, there was a oops event in Apollo 13, but that was nothing to do with rocket. It had to do with a command module and hydrogen fuel cell going kaput. So that, not hydrogen as in like the supercritical oxygen tank going kaput. So nothing to do with rocket. Rocket was awesome. And then let's contrast this to Starship. Now, Starship was launched in April 2023, not that long ago when I'm making this video, but the numbers are huge. They went from IFT Integrated Flight Test 1 to Integrated Flight Test 9, and all of them failed. Basically, none of them put a payload into orbit, even dummy payload. That's the problematic part. Because here's the deal, it does not matter how many times your rocket goes kaput when you're trying to land it. Because here's the deal, people are not paying you to land the rocket, people are paying you to put the stuff in orbit. Meaning, if this puppy did a mission and rocket landing failed, nobody would care. It won't even be in us. Yeah, they tried to recover it, it did not work. But payload went to the orbit, other people will book the rocket, nobody will have any issue. But if you have the same issue 9 times, meaning you did not put any mass in orbit, ooh, 9 times is like starting to be like, something is spicy here. Not a good kind of spicy. So what are the challenges? Why the heck a company that was so good, and like again, Falcon 9 is really good, and the fact Falcon 9, Falcon Heavy, and even Falcon 1 did not have this many boom events, what the hell is going on? Well, they're pushing each aspect of the craft in one go. That's the problem. Meaning they want one thing to basically become Starship, Millennium Falcon, basically they want in one go, in one project. That's the problem. So before they basically came down to Earth, they were smoking, and they were wanting to make this Starships basically interplanetary transport system. So the ITS system, this was their first system, and it was so bonkers, so huge that once they actually started to build, and again they built fuel tanks for it, carbon fiber fuel tanks. It's just they realized the full calculation and all that. It's like, yeah, no. So what you see when you are looking at Starship is just miniature version of this puppy. Basically, they shrank this puppy down as much as possible and still retained the capability, so to say. So that's why Starship looks like it came out of nowhere. It's because the design work was done on this mathematics and calculation and all that, and they were done based on carbon fiber, not stainless steel. So they had that design and they scaled it down, and they're like, because of cost, they switched into stainless steel. So okay, that's the core philosophy of it. So what do they want to do? What are their deliverables? Second stage reuse. That's a bold thing, but logical thing, given the fact that you have already sorted stage 1 recovery, stage 2 recovery, awesome. Massive mass and volume to orbit. Yeah, this is where it's problematic. It's like, if you want to do second stage reuse, even doing that to Falcon 9 itself would be more than like shut up, take money. Like shut up, take money. You do not have to do like massive mass and volume in the first time you are trying to do second stage reuse. It's like, okay, you're pushing it, but okay. And then you want rapid reusability like aircraft. Yeah, there's like the core problem. Because again, that's why stainless steel is chosen, because it solves this part of it. Rapid reusability like aircraft. And then they wanted to make sure it's super cheap. Yeah, the stainless steel takes care of that, takes care of the rapid reusability, but it kaputs everything else. Meaning your massive mass and volume to orbit goes away. Meaning you can't launch enough mass. I'll explain that part further. So there lies the core problem. You have too many things in one system. And what's the context? This is the first rocket system that's supposed to do all this, and this is the second in line. Basically, it's just after Falcon 9. It's like not enough time has passed where you have that kind of image. It's not like Falcon Heavy can actually carry 60 ton. If you put 60 ton, it will collapse the second stage, so to say. It's not actually, it has delta V. It has the like throwing heat energy, but does not have the like, I can carry 60 ton. It's not designed to do that. And again, that's why directly going from, let's just say 20 ton to 150 ton, it's like, bro, too much big of a jump. Even if 50 ton or even 60 ton, let's just say 50 ton would be good enough. If 50 ton, but again, 50 ton reusable, awesome. Mass, awesome. Volume, awesome. But 150 ton is like, whoa, 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 whoa. And again, we have done that. That's Saturn V. But problem is Saturn V is not reusable. You want reusable. So many contradictory variables in one project. Yeah, that's like too much deliverables. It's like, young programmers are like, yeah, I can do this, I can do that, I can do that. It's like, then you actually start with them. It's like, it has been 18 years. So same thing. And why it's such a difficult thing? Because chemical energy in propellant is fixed. We know, and again, the fixed part is theoretical maximum. You're never going to get that much. So that creates a fundamental, that's why they were using basically carbon fiber in original calculations. So compare that to other companies. For example, Rocket Lab is like, we built first rocket that is super cheap, carbon fiber based, battery powered turbo pumps. We cool, we got this, we got a rocket company going. We are the only company that actually has any cadence that looks like a modern rocket company. Cool, awesome. They're like, okay, what do we have to do? We have to make it reusable. Cool, awesome. We have to make it better than Falcon 9. Cool, awesome. Do we have to do second stage reuse? Not necessarily. What do they do? Okay, make sure this puppy has very good power to weight ratio because it's carbon fiber, and basically fairing. If you recover fairing, you already turbocharge against Falcon 9. Fairing recovery is done in one step, no problem, awesome. Reusability. Again, don't land it on the sea, directly land it on the land. It's far more efficient. And again, yes, now they are saying that they can have a boat, but most likely it's from some venture capitalists like, yeah, keep that as an option for somebody who needs far more delta V. So that gives them that option. But again, you do not want to land on the sea. It's cost too much. Again, the asset, the running cost and all that goes up too much. Not from the rocket point of view, but the auxiliary system you need. So that's why they are designing it. It's like, okay, we have Falcon 9. What if the fairing was improved? What if second stage was so simple, so lightweight that it was super cheap to throw away? So improvement. And then you look at stroke space. Like, okay, what if we design a different system that can use heat shields that is made out of stainless steel and like, high quality metal, and you have hydrogen running through it. And again, they had to choose hydrogen. Nothing else was there that can give that kind of oomph. And again, they are not trying to put massive mass and volume to orbit. They are just focusing on second stage reusable. So you see, these approaches are what we call your second project approach. Not, okay, let's do this, let's directly build Starship. It's like, yeah, that's again, you could have done that if there was no limitation in chemical propellant, but we know the chemical limitation of propellant. So that's why this is so challenging. They're just like pushing too much too quickly. And like, I'm going to do this, I'm going to do that, I'm going to do this. It's like, come down, man. So what are the pain points here? The pain point is use of 301 stainless steel. So compare that, like what is the alternative? Alternative, if you look into Falcon 9, they use something like this or exactly this alloy, lithium aluminum alloy. Almost all rockets are made out of that. either that or carbon fiber. So this is 2195 series. Now switching from lithium aluminum alloy to stainless steel was very hard decision. Now it did solve certain problems, but problem was mass. Meaning this goes from 301 gives you around 7.9 grams per cubic centimeter. Cubic centimeter, and compare that to lithium aluminum alloys 2195 series, that is 2.7, exponentially lighter, and again strong enough. How do we know? Falcon 9. So there lies the core problem. Now again, then why did they choose it? Well, two things. Cost, awesome. It's quick reusability. It solves the cost part, and it also reinforces the reusability part. Why? Because steel has better thermal softening. Meaning when you are talking about a steel, you might think, okay, you heat it up, it goes from solid to liquid. That's not what happens. It goes to elastic first, which we call thermal softening. So you have an I-beam and you start to heat it up, and let's say it can handle 1500 degrees Celsius before melting. Does not mean it remains a solid I-beam at 1500 degrees Celsius or 1400 degrees Celsius. It starts to become hulululu rubber band at 600 degrees Celsius. Now, is that 600 degrees Celsius good? Yes, compared to lithium aluminum alloy, that puppy only goes to 200. That's why it requires a lot of heat shielding material in the lower back end, which is completely blacked out. For that reason, meaning if they build Starship booster with a lithium aluminum alloy, can they do it? Of course they can do it, and it will be expensive, and in terms of reuse, it will put faith on heat shield rather than just the steel, like, I got this. So steel is like, I got this, but aluminum is like, no, I don't got this, you have to cover this puppy up. So there lies the contradiction there. And you're like, okay, what if they use titanium? Titanium improves it, but not that much. But it does have like the reusability part. It brings back reusability. So titanium can be used, but it's ludicrously expensive. Like titanium of that size, that mass is like, that's expensive enough for Elon Musk. That's like expensive. But again, it still would not have the oomph required of stainless steel. So now, what does this mean? Okay, we got the density, we got the reason. What's the problem here? Problem is rocket equation does not like mass, specifically dry mass. Ideally, your dry mass of the rocket would be 0. You just launch the fuel cell, it just disappears. But again, since we do not live in that world, what effect we're gonna have? Take the exact same engines, exact same rocket, Falcon 9 booster, and if you make it lighter, which again, from going from stainless steel to lithium aluminum alloy, let's say you successfully managed to reduce 44% of the mass. Can that be done? Of course. But again, it can easily be done to 50%, but you can't go that low simply because you have to give some buffer for heat shields in the lower area. But let's just say we put that 44%. Let's just say a good number. Why? That puppy will give you 1 kilometer per second extra delta V. It's not that you reach that speed, you get that speed on top of your current speed. That's why dry mass matters, and using stainless steel for dry mass, again, that's not a problem if you do not want to reuse. If they're like, okay, we use stainless steel, it's cheap, and we're gonna throw the rocket away. It's like, shut up, take money. But you're like, okay, we're gonna use it, it's cheap, but we want to reuse it. Now the mass is like, whoa, 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 whoa. So there lies the core problem. This is the core pain point in every design, every article I have looked into it, every basically core reason why the rocket behaves such a way. And what's the penalty of it? Thrust to weight ratio, meaning this engine was 100% useless. The flat rocket bodies can't take any ton to orbit. 2 was like, yeah, it's almost like Falcon Heavy would be better. Yeah, this puppy. And their whole hope is in this. Why? Because thrust to weight ratio. The rocket is too brutally heavy. If it was made out of lithium aluminum alloy, even with his shield, it would like, shwing. But right now it's like, Urgh. And problem with that is engines are in an unsafe condition, meaning balls to the walls. So that's really, really problematic. And again, that's why they're like, okay, we have this many engine. Yeah, this is not gonna work. We have to add more engines. And again, that's why they keep switching the engine. Even though compare that to Falcon 9 project development, it's like it was not that difficult. It's difficult because again, the core mathematics is done for carbon fiber, and they're like, okay, what if we put stainless steel? It's like, you can put stainless steel, but now you're hoping for magical rocket engine. Because these engine, if pushed that hard, that brutally, it's almost like barely any amount of margin. It's like saying that, oh, it can handle engine air. No, it can't. And again, that's why all the systems are either going kaput, or the fact that you can't actually put a ton into low Earth orbit. Again, with 3, they're hoping, but again, the jump from 1 to 3 is not that significant. Jump from 1 to 2 is significant. 2 to 3 is like mild. So, and again, it will happen in all technologies. So, because again, the chemical propulsion limit is here. You are already here. You can only go this much. You can't touch this. So, basically, thrust to weight ratio is their main core weakness. That's why, like, what if we add more engines? It's like, eesh. So these are the core fundamental pain point because of utilizing aluminum, basically not using lithium aluminum alloy or carbon fiber. Carbon fiber made with this puppy, like, carbon fiber is like, bruh, just bruh. That's why they were so excited about that interplanetary transport system. Now, let's understand the gambling part of it. Now, here's the deal. Every company takes a gamble on their product. That's like, duh. That's like, duh. But when you are taking this many gamble in one project, it starts to push luck. Like, starts to push off faith, so to say. So starting a production on an unfinished design, that's a weird thing. Okay. Like, okay, you are building a rocket that you do not know. You're like, yeah, we are building this and we are figuring out how to do it fast. And then we are throwing the design away. Then we're going to build again. It's like, okay, you did that. Again, not too big of a risk. Then it's like building the factory for mass production first. That was mean. That was like tempting faith. That's just mean. And then it's like changing too many variables at once. That's why there's basically go back 2-3 version back. It's like, yeah, it's almost reaching successful landing to, yeah, it's going kaput when it's going to orbit. It's going kaput when it's trying to re-enter. It's like, what the hell? Yeah, too many variables for change. And he was like, Elon Musk, I was directly talking in the interviews. It's like, yeah, we have changed 50-60 things or maybe even more. It's like, all these three things, it's like, now you're not tempting fate, you are punching fate. It's like, I'm gonna get this way. It's like, and faith is like, bruh. So trying to do all these things in one system, in first time you're actually going up from like, single stage reuse to double stage reuse, is like, ooh. So, and again, it's great if it works. It's not great if it does not work. And again, that's why you understand why this many booms happen. And again, let that be very clear, the current boom, I do not think it's SpaceX fault. It most likely it's like the supplier's fault. Or if they actually caused an issue, then it's like a double whammy. Then it's like, yeah, the fates are like, yeah, no, this guy is smoking too much, man. Like, change one thing. Change two things. Don't go like YOLO on everything. It's like change hundreds of variables and figure out how the heck it works. So that's the problem. So what is their to-do list? Meaning they have to get these things done. Well, first, the best option they have scientifically is reduce the dry mass. That's the best solution. Yes, it will increase the cost, but that should not be an issue if your rocket A actually works. B, you can reuse it. Even if you can only reuse it instead of 100 times to 50 times, that's still short uptake money compared to everybody else. So it's like, bro, we good. We got this. That's the best solution they have. Another aspect is engines have to come down from overstress to understress. They cannot be like, and again, I have to say in terms of Blue Origin's design, they are very focused on that part. It's like, no, our engines have to be chill. They have to be like, chill, bruh, chill. Because you do not, like, again, you want your engine to ability to go turbo drift on it and like, Tokyo drift on it, but you don't want it to be there all the time. You're like, if one engine flames out, then all other engines like, I got you, fam. You do not want to like, I barely have it. No. So engine must not be stressed, too goddamn stressed. And like, we are literally having engine going kaput, literally in orbit, kaput. That's like, engines are like, bro, what are you doing? So, and payload deployment does need doors. They do not have good door design as of now. And pest dispenser, that's cool and awesome, but that limits them to Starlink project. Now, cool and all, but if you want other people's money, you have to accommodate other people. So door design has to be expedited and must deploy payload to low Earth orbit. That has to be prioritized. Has to be like, yeah, we have to deploy payload to orbit. Now you're like, okay, why the ASAP part? Well, if they do not, NASA does have funding and they can cancel it. SpaceX does have private funding that can be cancelled. And again, that's why the 9-time failures is a problematic part. It's like if they're like, oh, it took 2 years or 3 years, that's not an issue. 9 times going boom, 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 and it's like, move fast and break things. It's like, yeah, but not 9 times, not 10 times, and God forbid 20, 15 times. It's like, people will lose faith. And private funders are like, yeah, we cool, bro, but like, I think you flew too close to the sun in this one. So that's the whole point. So what can we expect? Well, you have to understand, if you are very young, you may not know Elon Musk used to smoke, I do not know what he used to smoke, something very dangerous, but he was actually trying to do this. This was a Red Dragon project. And you're like, wait a minute. He was stupid enough to think that? Yes. He actually was stupid enough to think that he can have a basically Dragon capsule, modify it a bit, not change too much, put it on Falcon Heavy, send it to Mars with humans inside. I'm like, dude, that's putting human in a coffin for 2 years. That's not acceptable. I have no idea what you smoked. Don't smoke it. That's not a good idea. That's like, you do not bring this to public. You do not bring this to NASA. But they did. And they were like, somebody bitch slapped them, thankfully. And they're like, okay, we're gonna shift delete it. Then they smoked this puppy. And he's like, yeah, what if we designed it this and all that? Basically, they reversed engineered it. That's the problem with this. Meaning they wanted a magical craft. It's like, okay, how do we make the magical craft? It's like, yeah, what if it's a like huge diameter? I'm like, not even joking. Some designs were like, what if we had 15 meters diameter? I'm like, Burj Khalifa, just launch the Burj Khalifa, man. At that point in time. So, and goddamn, engine counts for like something stupid, like 49 engines or something like that. It's like, what if we had this? Like, yeah, no. So, and again, the subtle smoking, where it's like, what if we have a flat ground? It's like, no, you do not put flat grounds. No matter how much water deluge you put into it, that was stupid, is stupid, will remain stupid. Thankfully, again, somebody bitch slapped him, and ta-da, we have a curve plate. Yay, logic wins. It's like, it's a sad part that we have to have this, but like the best example, like best hopeful, faithful explanation I have is that there was a basically licensing issue when you are talking about digging below the surface. That's the best explanation why he could thought like, what if we had just a flat plate? But again, NASA also had that issue with some launch site where they could not dig deep. They basically made an upwards trench. It's like, you do not put flat ground, because even if you can handle the heat, the sound waves do not behave nicely. Sound waves is like, nah, bruh, you put curve. So at this point in time, they have to seriously look into basically some change in approach. Again, like going from flat to this, going from stainless to something, or either refine the design such a way that is like super light. But I'm getting worried, because every discussion Elon Musk is having is like, what if we stretched it? What if we stretched it? It's like, what if you go to lithium aluminum alloy? You know how to do this. Just so core reason, that's why. And again, if the 10th one also goes kaput, yeah, then understand this. Everybody who's saying that it's too goddamn heavy is right. So they are all their bets are hoping on magical Raptor 3 engine's performance, which again, I'm not sure it will able to handle this kind of brutal load. And again, if one engine flames out, rocket will look like it's working. It just will not have the delta V. It's like, it will be bad. So this was my presentation on like what exactly is going on with this company that was successfully able to do everything, and now it's like keep booming 9 times. So hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.